ஆமா இன்னைக்கு.
எஸ் சார், நான் தான் பண்றேன் சார்.
ஆமா சார்,
நான் தான் சார் பண்றேன்.
கார்மல் பேசுங்க, உங்க வாய்ஸ் வரல. கார்மல் வாய்ஸ் வரல.
ஹெட்போன் எடுத்துட்டு
சார். அருசேவியர் சார்.
சார் சொல்லுங்க சார்.
இல்ல மத்த ஸ்டூடண்ட்ஸ் பார்ட்டிசிபென்ட்ஸ்லாம் ஜாயின் பண்ணிட்டாங்களா?
அவங்க எப்படி?
இல்ல ஃபேஸ்புக்ல சார், எல்லாமே ஃபேஸ்புக், யூடியூப் தான்
உங்களுக்கு. நம்ம ஒரு 7 பேர் தான், பேனலிஸ்ட் மட்டும் தான்.
ஓகே ரைட்.
சார் நான் பேசுறது தெளிவா கேக்குதா சார்?
கேக்குது.
ஓகே சார், தேங்க்யூ சார். ஹெட்போன் எடுத்துட்டு பேசினாதான் தெளிவா கேட்கும் சார். எனக்கு
ஜோலி மேடம், லேப்டாப்பா செல்போனா?
மொபைல் தான் சார்.
மொபைல் தானே? ஓகே.
ஆமா சார், லேப்டாப்ல சரியா வரல, அதனால மொபைல் ஆன் பண்ணி.
வராது சார், லேப்டாப் சரியா வராது.
ஆஹா,
எக்கோ.
ஏன் சார் எக்கோ?
இல்ல
ஓகே சார்.
பக்கத்துல யாரோ ஓபன் பண்ணிருப்பாங்க. ஹலோ, கேக்குதா? ஜூலி மேடம், நான் பேசுறது கேக்குதா?
சார் கேக்குது.
ஓகே சார்.
அதெல்லாம் அப்படியே இருக்கும். அதெல்லாம் செல்ஃபி இது வர மாட்டீங்களா
சார்? வந்து சார் வீடியோ தெரியுது
சார். வீடியோ
யாரு? ஹலோ,
நான் அலெக்ஸ் ரமணி பேசுறேன் சார்.
அலெக்ஸ், நீங்க பேர் சொல்லி சொல்லுங்க. என்கிட்ட பேசுறீங்களா? லாரன்ஸ் என்கிட்ட?
எஸ் சார்.
ஓகே. என்னோட வால்யூம் கரெக்டா கேக்குதா?
கேக்குது சார்.
ஏன் வீடியோ தெரியுதா
சார்? உங்க வீடியோ தெரியுது சார், உங்க வாய்ஸ் நல்லாவே வருது சார்.
ஓகே. ரிவர்ஸ் கேமரா
போர்டை மட்டும் செட் பண்ணிட்டு அப்படியே போதும் சார். ஓகேங்க சார்.
ஓகே. ரிவர்ஸ் கேமரா போட்டா வரும் இல்ல?
வரும் சார், கண்டிப்பா வரும் சார்.
ஓகே, போடு. ரிவர்ஸ் கேமரா
செக் பண்ணுங்க.
அது வேணா, அது அவங்க அட்ஜஸ்ட் பண்ணாதான் வரும். அது அப்படியே விட்டுறணும். அது கிடையாது. நீ ரிவர்ஸ் கேமரா போடணும், அவ்வளவுதான். அவங்க அட்ஜஸ்ட் பண்ணிக்குவாங்க.
உங்களோட போட்டோ மேல ரிவர்ஸ் கேமரா ஆப்ஷன் கொடுத்திருக்காங்க.
அப்ப இது அவ்வளவுதான்.
பெருசா அப்ப இது போட்டோ சென்ட்ரலைஸ் பண்ணுவாங்க. அப்பதான் நம்ம போட்டோ பண்ண முடியும்.
அன்னைக்கு நீங்க ரிவர்ஸ் மாத்துனீங்களே சார்?
ரிவர்ஸ் கேமரா போடுங்க சார்.
ரிவர்ஸ் கேமரா போடுறதுக்கு ஆப்ஷனே வர மாட்டேங்குதே.
அன்னைக்கு நீங்க எப்படி சார் பண்ணீங்க? டெஸ்ட் பண்ண அன்னைக்கு பண்ணீங்களா சார்?
போட்டேன், அன்னைக்கு போட்டேன். இன்னைக்கு போட முடியலையே. போனை வந்து நீங்க என்னோட போட்டோவை சென்ட்ரலைஸ் பண்ணீங்கன்னா தான் அது வரும். ரிவர்ஸ் கேமரா போடுறதுக்கு சென்ட்ரலைஸ் பண்ணுங்க பாப்போம். ஹலோ
சார்.
நீங்க அந்த போட்டோவை சென்ட்ரலைஸ் பண்ணீங்கன்னா, என்னோட போட்டோ சென்ட்ரலைஸ் பண்ணாதான் அது ரிவர்ஸ் கேமரா போடுறதுக்கு வரும்.
அப்படி வருதாங்க சார்? ஒரு நிமிஷம்.
ஆமா, இல்லாட்டி அந்த இது ஆப்ஷனே வர மாட்டேங்குது.
இப்ப பாருங்க சார்.
இப்ப
கேமரால வந்துருச்சு மேம். இப்ப தெரியுதா சார்? இது செல்ஃபி.
ரிவர்ஸ் போடு.
இதுக்கு பேசிட்டு சார் தெரியுதா மேம்? ஸ்கிரீன் எல்லாருக்கும் விசிபிள் ஆகுதா? நான் இப்போ ரிவர்ஸ்ல போட்டு செட் பண்றேன். இப்போ உங்களுக்கு கிளாரிட்டி நான் பண்றேன். கிளாரிட்டி பாருங்க. சரியா? இருங்க நான் கேமரா செட் பண்றதுக்குள்ள போது இப்ப தெரியுதா? பேக் போங்க. செட் பண்ண
சார் இப்ப ரிவர்ஸ் கேமராவா சார்?
ரிவர்ஸ் கேமரா.
ஓகேங்க சார்.
ஓகே ஓகே சார்.
சரியா இருக்கா? நான் கணிக்கை லாரன்ஸ்
சார்
ஓகே சார்.
ஓகே ஓகே சார்.
ஓகே 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 ஃபைன்.
ஓகே
இல்ல
சார் இந்த
சார் ஜோயல் ராய் சார், உங்க கேமரா சரியா தெரியல. ஜோயல் ராய். எஸ் சார். இப்ப சரியா இருக்கு.
கணிக்கு சார், நாராயண் சார் கொஞ்சம் செட் பண்ணிருங்க சார். கணிக்கு சார்
சொல்லுங்க.
லாரன்ஸ் சார் செட் பண்ணிடுங்க, பாத்துருங்க. அதான்
லாரன்ஸ் சார் சரியா தான் இருக்கு. அது ஓகே.
ஓகே 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 சார்.
சார் ஜோயல் சார், உங்க வீடியோ கேமரா கூட நீங்க ஆஃப் பண்ணிக்கலாம், தேவையில்லை.
ஆமாம்.
கடைசியா ஓட் ஆஃப் தேங்க்ஸ் சார், அப்ப நீங்க ஆன் பண்ணிக்கலாம்.
ஹலோ கார்மல் சொல்லுங்க. கார்மல்
கேக்குதா சார்?
கேக்குது. ஜோயில் தான் கேட்க மனுச்சு அவர் செக் பண்ணிங்க. கடைசி நேரத்தில் தான் எடுப்பது. அவர் ஓட் ஆஃப் தேங்க்ஸ் சொல்லல. ஜோயில் மட்டும் செக் பண்ணிடுங்க. ஜோயில் சார் செக் பண்ணிட்டீங்களா வாய்ஸா?
சார் ஜோயல் சார், நீங்க போன் எதை அட்டெண்ட் பண்ணிருப்பீங்க போல, கட் ஆயிருக்கு. நீங்க லாக் அவுட் பண்ணி லாகின் பண்ணுங்க, சரியாயிடும்.
கார்மல் சொல்லுங்க.
இடையில போன் வந்தா எடுக்காதீங்க. ஜோயல் சார், நீங்க லாக் அவுட் பண்ணி லாகின் பண்ணுங்க.
ஜோயல் சார் கேட்க மாட்டேங்குது. கார்மல் சொல்லுங்க.
இடையில போன் வந்தா எடுக்காதீங்க.
கணிக்கு சார், கார்மல் சார் சொன்னா ஜோயல் கேட்க மாட்டேங்குது. அவருக்கு கார்மல்
கேட்டுட்டு இருக்காரு.
கேட்டுட்டு இருக்காரா? சரி சரி சரி
சரி ஓகே. 9:14 ஆயிடுச்சு, நம்ம ஆரம்பிப்போம், அப்புறம் பேசிக்கலாம்.
ஓகே சார்.
எஸ் சார்.
Julia madam, ready?
Yes, sir.
Okay. Begin. Start.
The joy of life comes from our encounters with new experiences, and hence there is no greater joy than to have an endlessly changing horizon. For each day to have a new and different sun. Greetings to all. I, Dr. P. Julia Mary, welcome you all to the 2 days webinar on CSIR problem-solving techniques in algebra and analysis. On behalf of the Department of Mathematics, St. Joseph's College, I welcome you all. I can do all things through Him, who gives me strength. We'll start the session with the prayer song.
There shall be showers of blessing. This is the promise of love. There shall be seasons refreshing. Sent from the Savior and I. showers be There shall be showers of blessing, precious reviving again, over the hills and the valleys, sound of abundance of rain, showers of blessing, showers of blessing we need. Mercy drops showers are falling. Look for the showers we feel.
I am pleased to welcome Professor A. Arul Xavier, Coordinator, Shift 2, Department of Mathematics, St. Joseph's College, to give the welcome address.
Good morning to one and all. I cordially welcome you all for this webinar. We do this is the greatest glory of the God. I pray to the God Almighty to bless us all. I place heartful thanks and welcome to the Jesuit Management, Reverend Dr. Leonard Fernando S.J. Rector, Reverend Dr. Peter S.J. Secretary, and Reverend Dr. Aragasamy Xavier S.J. Principal, St. Joseph College, Trichy, to kind enough to accept the department regulations regarding conduct of webinar and providing all technical facilities. Welcome you, Reverend Fathers. With the great pleasure, I offer cordial welcome to Dr. Alex Ramani, Deputy Principal, Shift 2, St. Joseph College, Trichy. Welcome you, dear sir. With immense pleasure, I welcome today's speaker, Dr. Lawrence Joseph Manohar, retired former HOD, Department of Mathematics, St. Joseph College, Trichy. Welcome you, sir. I offer special thanks and welcome to Dr. Kanickai Raj, Coordinator, Department of Physics. Welcome you, sir. With great joy, I welcome Dr. T. Rajaratnam, HOD, Department of Mathematics. Welcome you, dear sir. I welcome Dr. P. Lawrence Rosario Raj, Vice Principal, Shift 2, St. Joseph College, Trichy. With a great pleasure, I offer cordial welcome Professor J. Mercy Arokirani, convener of this webinar. It is my privilege to offer pleasant welcome to the professors of Department of Mathematics, St. Joseph College, Trichy. Welcome you, dear professors. I also welcome the participants from various institutions. Welcome you, dear professors, scholars, and students. Once again, I welcome you all. Thank you.
Thank you, sir, for your warm words of welcome. Now I request Dr. V. Alex Ramani, Deputy Principal, Shift 2, to felicitate our webinar.
The most respected Reverend Father Rector, Reverend Father Secretary, and Reverend Father Principal, esteemed resource person of this webinar, Professor Dr. Lawrence Manoharan, formerly of our college, revered Coordinator of the Department of Mathematics, Shift 2, Dr. Arul Xavier, the most revered Nodal Officer of this webinar, Dr. Professor Kanickai Raj, Department of Physics, respected Madam Mercy Arokirani, the Organizing Secretary of this webinar, and her team of the Organizing Committee, in Mr. Joy, respected Vice Principal of Shift 2, Dr. Lawrence Rosario Raj, revered professors of Department of Mathematics of our college and other institutions, my dear beloved students and scholars who are participating in this webinar. All of you, a very pleasant good morning. I feel I'm very much honored to be part of this webinar. I sincerely offer my thanks to the organizing committee for giving me this wonderful opportunity to give the felicitations at the inauguration of this webinar. I feel it is a very rare privilege given to me. Though we are in the lockdown period, our learning is not locked down. We have explored a better way of learning through online by this kind of webinar or video conference. This webinar on problem solving techniques is very relevant and it is the need of the hour. This webinar will sure to empower the aspirants of CSIR, NetSet and other competitive examinations. The students and scholars will get enriched their problem solving skills such that they will be able to crack the examinations successfully going to face in the future. The problem solving skill is the most important life skill. We not only find problems in our study subjects, but also day-to-day life. Thus, problem solving skill will help us to be successful persons in our real life situations. A person who has a very effective problem solving skill is also possessing other related skills like creative thinking, or we say out of box thinking, team working, emotional intelligence, risk taking, and decision making. These are the related skills with the problem solving skill. When we say a problem, how do we understand a problem? Anything that is doubtful or difficult to understand or hard to accomplish or hard to deal with that needs a solution or a way out is a problem. All problems essentially have two features. One is the goal, or we say answer or solution. The second one is the barrier or hurdles, or we say twists. Any problem is solved through 6 important steps. One is identifying the problem or knowing the nature of the problem. The second one is structuring the problem or keenly observing the problem to find the facts related to the problem. Thirdly, looking for possible solutions. Fourthly, choosing the best possible solution. The fifth one, putting to use the best possible solution. The sixth one is monitoring or seeking the feedback. These are the essential steps involved in any problem solving method. Thus, today's webinar will throw more insight on solving problems very pertinent to our subject of study, mathematics. We have with us the great mathematician, Dr. Lawrence Manoharan. He is a modern teacher. He has rich experience in teaching mathematics at the UG and PG levels. He is a great scholar in mathematics research. He is a national level unionist also. He was heading the ACTA unit of our college some years ago. A multifaceted personality. Such a resourceful, scholarly academician is here with us today. He is going to enlighten us on the problem-solving techniques in mathematics. We are fortunate enough to listen to his proficiency and scholarly approach. On behalf of all of us, I sincerely welcome and thank our Professor for his generous gesture in sharing his experiences and expertise with us through this webinar. I'm sure that all of us will get enriched in problem solving skills and we will become successful persons in life. I'm happy that the Department of Mathematics Shift 2 has taken initiative in organizing this webinar. This is a sign of growth. Any new beginning is a sign of growth. I wish that these initiatives will grow the department in the days to come. With this brief introductory remark, I wish you all the very best. Thank you very much. Have a good day and purposeful day. Thank you very much. Thank you.
Thank you, sir, for your words of motivation. I request Professor J. Karmal Pushparaj, Assistant Professor, Department of Mathematics, Shift 2, to introduce our distinguished resource person.
Warm greetings to all. It gives me immense pleasure to introduce our beloved Professor, Dr. R. Lawrence Joseph Manogaran, former head, Department of Mathematics, St. Joseph's College, Trichy. He has completed his MSc in IIT Madras. After completing his MSc, immediately he joined as a lecturer in St. Joseph's College in 1974. He also obtained his MPhil and PhD as a part-time in St. Joseph's. He has published more than 20 research articles in the reputed journals. After his retirement from the 37 years of regular service in 2011, he is a well-known trainer for students and faculty to clear CSIR NET, GATE, SET examinations in mathematics. Every year, more than 20 students cleared the CSIR NET and SET exam guidance and training. He is well versed in real and complex analysis, algebra and linear algebra. Dr. Aral is always ready to help those who are preparing the competitive exams. While Dr. Aral is working in St. Joseph's, every student knew his phone number and address. Many of us used to visit his home in Trichy. Participants are requested to feel free to contact him if you have any queries. Today he is going to discuss about fundamental spaces and problems in linear algebra. Thank you all. Over to you, sir.
Thank you. Good.
Good morning, all of you.
Good morning, sir. Good morning, sir.
At the outset, I would like to thank the management of St. Joseph's College for giving this opportunity to me to be a resource person for this webinar. A host of distinguished faculty of St. Joseph's College, they are organizing this seminar, the webinar, starting from Alex Ramani, Lawrence Rosario. There are so many persons organizing this, Mercy, Julia, Carmel, and so many others. I congratulate all these people for the pains they have taken to organize this webinar. And this has become a feature in higher education. Webinar education has become a distinguishing feature of higher education. Not only because of Corona, but because of the advancement in technology. This has become the order of the day. webinars of this kind are going to play a very crucial role in higher education. Even PhD Viva OC examinations, MPhil Viva OC examinations are all held using webinar. And this is going to be a feature in higher education in the years to come. So, I am going to give you something about fundamental spaces in linear algebra. I am going to stick to the basics. It is not going to be difficult at all. I am going to stick to the basics. See, I am starting with the definition of a matrix. Matrix. See, in high school, we define a matrix as a rectangular array of numbers. And they stopped with that. But a matrix is not just a rectangular array of numbers. You must know a matrix has life. Actually, it is a function from one set to another set. So when you are asked to define a matrix, you must say it is a rectangular array of numbers which has a lot of life. It is actually a function from one set to another. For example, supposing I take a matrix like this. I am taking a matrix with 3 rows and 4 columns. Now this matrix is actually a function from, see, it is actually a 3 by 4 matrix. So it is a function from R4 to R3. It is a function from R4 to R3. It will convert any 4-dimensional vector into a 3-dimensional vector. That is what this matrix does. For example, supposing I take A of 1, 0, 0, 0. This is a 4-dimensional vector. 4-dimensional vector. A of 1, 0, 0, 0, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6 into 1, 0, 0, 0. This is equal to, now we multiply the usual matrix multiplication, first row into this vector. So it is going to be 1, then 2, then 3. So a 4-dimensional vector 1, 0, 0, 0 is connected to a 3-dimensional vector 1, 2, 3. So the matrix is converting the 4-dimensional vectors into 3-dimensional vectors. It is called a function. It obeys all the conditions of a function, and it is a function. And it is not just any ordinary function. It has got very special properties. A matrix is a linear function. It is a linear function. What is that? A of x plus y will be equal to A of x plus A of y. A of alpha x will be equal to alpha ax. Any function which obeys these two conditions is called a linear function. So what are x and y? They are two vectors in the domain. A of x plus y must be a of x plus a of y. A of alpha x must be alpha x. What is alpha? Alpha is a scalar. It's a scalar. So the matrix satisfies these two properties, and that is why it is a linear function. So remember, when you are asked to define a matrix, you must be very careful, because matrix plays such a very important role in mathematics, not only in linear algebra, in algebra, in every application, in differential equations, in graph theory, wherever you go, in any branch of mathematics, matrix plays a very, very important role. It is found in every branch of mathematics. So, a matrix is actually a function, an m by n matrix, having m rows and n columns. It is a function from m by n matrix. It is a function from Rm to Rm. So this is what you have to remember very carefully. You have to remember this very carefully. Now, with this matrix, we are going to associate the four fundamental spaces. The four fundamental spaces. Of course, I am taking the definition of a vector space for granted. I am not going to define a vector space, because that is a different chapter altogether. So, I am going to deal only with the fundamental spaces, but the fundamental spaces are also vector spaces. They are all vector spaces. They are all actually subspaces of the domain and codomain. The fundamental spaces, there are four fundamental spaces. They are subspaces of the domain and codomain. That is what I am going to define now. So you take any matrix A. Once again, I am going to take the same example. 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6. And this matrix A, it is going to be a function from R4 to R3. Remember, it is a 3 by 4 matrix with 3 rows and 4 columns. So, it is a function from R4 to R3. First, what is kernel of A? Null space of A. All these are one and the same. Kernel of A, the definition, kernel of A, it is the set of all x in R4 such that Ax equal to 0. It is a set of all x in R4 such that Ax equal to 0. This is also called the null space of A. And then what is the image of A? Image of A, it is the collection of all Ax, x belonging to R4. So once you have a matrix, immediately with that matrix, we are defining two sets associated with that matrix. One is kernel of A. Kernel of A is the set of all x in R4 such that Ax equal to 0. Image of A is the set of all Ax. It is also called the range. So image of A is Ax, x in R4. Now we can easily prove that kernel of A is a subspace. It is a vector space. It is a vector space. It is a subspace of the domain. Image of A, it is a subspace of the codomain. So the function is like this. The matrix is like this. Usually the domain is denoted by a circle. The domain is denoted by a circle. The codomain is also denoted by a circle. So this is not a universal representation. This is not a universal diagram, but most of the authors follow this. The domain of any matrix denoted by a circle, codomain also denoted by a circle. Now, kernel of A is found in the domain. So the matrix A, it goes from Rn to Rm. So here I am assuming A to be m by n matrix. A is an m by n matrix. And it is a function from Rn to Rm. So kernel of A will be a subspace. It is a vector space. It is a subspace of the domain. So it is usually denoted by a horizontal rectangle. This is kernel of A. The image of A, it is going to be here. It is going to be in the codomain. It is a subspace of the codomain. It is also a vector space. It is usually denoted by a vertical rectangle. This is image of A. This is image of A. It is also called the column space of A, C of A. The image is also called the column space of A. Now, given any matrix A, you have its transpose, A transpose. A transpose will be a function from Rm to Rn in the other direction. So it will be in this other direction. A transpose will be a function in the other direction. The domain of A transpose will be Rm. The codomain of A transpose will be Rn. The roles will be reversed. The roles will be reversed. So it's a function in the other direction. So this matrix A transpose also has a kernel that will be here. That is always denoted by a horizontal rectangle. What is this horizontal rectangle in Rn? That is the kernel of A transpose. This is kernel of A transpose. This A transpose will have an image. The image will be here. That is denoted by a vertical rectangle. Image of A transpose. It is also called the row space of A. It is called the row space of A. Or it is called the column space of A transpose. So now you have to clearly understand these four rectangles and the two circles that I have. When you understand these, then the chapter on fundamental spaces will be very, very easy for you. So I want to repeat. You have a matrix here, a matrix m by n matrix is given, m by n columns. Always the matrix will be assumed to be m by n, unless otherwise stated. You have m rows and n columns, and for m. The matrix will be a function from Rn to Rm, any m by n matrix. With this matrix A, we are going to associate four spaces. One space is the kernel of A, another space is the image of A. And then two spaces are going to be associated with the A transpose. They are also called spaces associated with A because we say they are associated with A. Kernel of A transpose and image of A transpose. So you must remember the kernel of A and kernel of A transpose, two rectangles in the domain which are perpendicular, which are orthogonal. very meaningfully, very knowledgeably, I have drawn the rectangles to be perpendicular. It is not as though it is. And with A, I am going to associate four spaces. Four spaces. What are the four spaces? One is the domain is always denoted by a circle. The codomain is also denoted by a circle. This is Rn, this is Rm. The kernel of A is a horizontal rectangle here. The vertical rectangle in the domain is the image of A transpose. This is A transpose, image of A transpose. And the horizontal rectangle here is kernel of A transpose. The vertical rectangle is image of A. This is image of A transpose, kernel of A. So these are the diagrams you have. So remember, these two are the vector spaces. They are subspaces of the domain. These are also subspaces of the codomain. There is another component here outside these two rectangles that will represent vectors which are not in kernel, which are not in image, but which are linear combinations of vectors here and here. So any vector here, if I take a vector x there, in the circle, but outside the two rectangles, it will be a vector which is a linear combination of the vector in this rectangle and in this rectangle. Similarly, here also you have the third component. If I take a vector y here, it will be a linear combination of a vector here and a vector here. So remember that the rectangles are subspaces, they are vector spaces. But the third component, it's not a vector space. It's not a vector space. And the most important theorem in linear algebra, the fundamental theorem that is called rank A plus nullity A equal to n. Rank nullity theorem, it is called the rank nullity theorem. Rank of A plus nullity of A equal to n. The rank of the matrix plus the nullity of the matrix is n. What is n? N is the number of columns. N is A. Or n is the dimension of the domain space, domain vector space. So this is rank of A plus nullity of A. Rank of A is a number. It's a number. Says if you add this dimension and this dimension, so this dimension, the dimension of this space, vector space. So note that the third component, which exists outside, has no. It's not a vector space. It has no dimension. Only vector spaces have dimension. So there are not a lot of results which are to be proved. For example, the rank nullity theorem. That's a fundamental theorem starting. Now, look at the rectangles. The rectangles are perpendicular to each other. That means any vector here is perpendicular to any vector here. If I take any vector in the vertical rectangle in the domain, it is orthogonal to, perpendicular to any vector in the kernel. So if I take x here and y here, X dot Y will be 0. The dot product will be 0. X dot. Similar thing happens here also. If you take any vector here, X, and any vector Y here, X dot. Now all these things can be proved. One more important thing to be proved is the function A will be 1, 1 on this vertical rectangle. On the vertical rectangle in the domain, the function A will be 1, 1. And the vectors common to kernel and image, the vertical rectangle and the horizontal rectangle, only the 0 vector will be common. Only the 0 vector will be common. Because only the 0 vector is perpendicular to itself. A non-zero vector cannot be perpendicular to itself. A non-zero vector cannot be perpendicular to itself. So only the 0 vector is perpendicular to itself. So 0, that is the intersection of these two rectangles, that is common to kernel and image A transpose. No other vector will be common. Because every vector here is perpendicular to every vector here. Now let me do a very small problem to explain the kernel and the image. For the same 3 by 4 matrix, say, let me take this matrix A, once again the same matrix 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6. I want to find the kernel of A. The kernel of A. So what I do is, I'm going to perform elementary row operations. Elementary row operations. 3 operations are called elementary row operations. One is interchange of rows. Interchange of rows is allowed. Next, second one is multiply a row by a non-zero number. Multiply any row by a non-zero number. And the third one, second one is called scaling. Third one, add k times row I to row j. Add k times row I. And that is, you are multiplying row I by k and adding it with row j. That is rj plus k times ri. Here k can be 0. If k is 0, you won't get anything new. So rj plus kri, that is ith row is multiplied by a non-zero number k and added with the jth row, and this replacement has to be in the jth row. Jth row goes to rj plus kri. So these 3 are called row operations. By performing a series of row operations, you can always find the rank of any matrix. You can find the kernel of that matrix also. The kernel of the matrix can be found by performing the row operations. I'm going to quickly do that. So this is equal to, the row operations may look very simple and childish. It is not. You have to be very careful. If you don't follow the rules carefully, you will not be able to proceed. You will get stuck up. So, first row is written as it is. The second row, so, and below the pivot, all must be made 0. all the subtract it from the second row. So what I am doing is R2 minus 2R1, R2 minus 2R1. So the second row minus 2 times the first row, this is 2 minus 2, 0, 3 minus 4 minus 1, 4 minus 6 minus 2, 5 minus 8 minus 3. This entry also must be made 0. So third row minus 3 times the first row. 3 minus 3 is 0. 4 minus 6 is minus 2. 5 minus 9 is minus 4. Minus 6. This is 1, 2, 3, 4. Let me make all these positive by multiplying by a minus sign. 0, 1, 2, 3. 0, 2, 4, 6. So this is a pivot. Now in the second row, look for a pivot. That is the first non-zero number is called a pivot. First non-zero number is the pivot. And there is a rule to be followed for the pivot. The pivot in any row should be to the right of the pivot in the previous rows. That is the rule you have to follow. The pivot in any row should be to the right of the pivot in the earlier rows. So this pivot is to the right of this pivot. So that is allowed. So this is equal to, now below the pivot I will get 0 here. So I multiply this row by 2 and subtract. So I get 1, 2, 3, 4, 0, 1, 2, 3, 0, 0, 0, 0. When I multiply this row by 2, the entire row gets cancelled, 0. So I get 2 pivots. The pivots give you the basic variables or the pivot variables. The non-pivots will give you the free variables. These are the free variables. They are the free variables. For the free variables, values can be assigned. There are 2 free variables. I have to give the value 1, 0 and then solve. So this is x3, this is x4. Remember x1, x2, x3, x4. x3 and x4 are the free variables. So for x3 and x4, I must give the values 1 and 0. Then for x3 and x4, I must give the value 0 and 1 and solve. That will give me 2 solutions. Those solutions will belong to the kernel of A. For example, I am putting x3 is 1 and x4 0. So here in this equation is x2 equal to 0. So I am going to put x3 1 and x4 0. So this is 1 and 0. So x2 will be equal to minus 2. x2 will be equal to minus 2. The same value 1, 0 I have to substitute here. 1 for this and 0 for this. So x1 plus 2x2 plus 3x3, that is 3, plus 4x4, that is 0, equal to 0. So x1 will be equal to, x2 is already found out to be minus 2. So minus 2 into 2 is minus 4 plus 3 equal to 0. So x1 is equal to 1. So let me write the solution correctly. x1 is 1. x2 is minus 2. x3 is 1. x2 is minus 2. 1 minus 2, 1, 0. So this is a solution. So 1 minus 2, 1, 0 belongs to kernel of A. One more solution is possible. How to get that solution? I have to put x3 0, x4 1 and solve these two equations. The reduced equations. I have to solve these reduced equations. I will get one more equation. That vector will be linearly independent of this vector. So the next vector I get along with this vector, they will be linearly independent. So in linear algebra, whenever we talk about vectors, we will be interested only in linearly independent vectors. When the vectors are linearly dependent, they are useless. So there will be two linearly independent vectors. So for this matrix A, the kernel contains two vectors. One vector is this. Now similarly, I can find AX, the column space. The column space. So remember that this is my domain. So here you have the vertical rectangle and the horizontal rectangle. In the horizontal rectangle, I have found out only one vector. 1, -2, 1, 0. Of course, another vector can be found out. Similarly, I am not going to do that. Now, in the codomain, I have and a rectangle. The codomain. Now, the vectors here, they are in the range. They are in the range. So, they will be in the form AX. 2, 3, 4 will be here. 3, 4, 5 will be here. 4, 5, 6. All the columns will be there. All the columns will be in the vertical rectangle. They will be in the range. They will be in the range. They will be in the range. Now, the span of all the four columns, that will give you the space. The collection of all linear combinations, that will give you that image. So, because this is of dimension 2, see, already I have told you, there are two linearly independent vectors in the kernel. Only one I have found out, the other one can be similarly found out. 2 here, this also has to be 2, because 2 plus 2 will be the dimension 4. This is dimension 4, this is dimension 3. So this has to be 2. That means out of the 4 columns, only 2 columns are linearly independent. The other columns are useless. They are all dependent on the earlier columns. So here you will get 1, 2, 3 and 2, 3, 4. We are the linearly independent columns. The other columns will be there. They will be the but columns. So the dimension this 2 plus the dimension of the kernel, that is also 2. 2 plus 2 equal to the whole dimension 4. Now what is this? This is the row space. The row space. So row space. So there are 3 rows. There are 3 rows. So remember, this is 2. When you add this, you must get 4 again. You must get, because the dimension of this vertical rectangle and the dimension of this vertical rectangle, they will be equal. Here also you will get only 2. So 1, 2, 3, 4. It is a row, but you have to write it as a column. You have to write it as a column. Because always the vectors are written as columns. Then 2, 3, 4, 5. And 3, 4, 5, 6. So there are 3 rows. These 3 rows have to be written as columns, column vectors, and all these 3. But out of these 3, only 2 are Li. Only 2 are Li. Because already the dimension is 2 here. The dimension will be useless. linearly dependent. So only 2 are there. So 1, 2, 3, 4. The other one is 2, 3, 4, 5. You have to write that. So these two vectors will span the vertical rectangle in the domain. And you must note that these two vectors will be perpendicular, orthogonal. See, 1, 2, 3, 4. And 1, minus 2, 1, 0. They will be orthogonal. This is U, this is V. U dot V, U dot V. Multiply 1 into 1, 1. Plus 2 into minus 2, minus 4. 3 into 1, 3. 0 into 4, 0. You have to get 0, otherwise you have committed some mistakes. So the rows, when they are written as vectors, column vectors, they will all be orthogonal to any vector in the null space, in the kernel. This will be true for any vector here and any vector here. So they are orthogonal. That's why I have drawn perpendicular rectangles. The intersection will have only the origin. Here also the same thing. Now, just a small problem before we take up the list of problems which I have already given to you. Now, what happens when the rank is n? See, A is an m by n matrix. A is an m by n matrix. That means A is a function from Rn to Rm. So, draw the rectangles. This is Rn, this is Rm. What happens when the rank is n? Rank of A equal to n. What happens when the rank of A equal to n? When the rank of A equal to n, that means this dimension is n. The whole dimension is n. That means this rectangle will shrink to a point. It will be just the origin. This rectangle will not exist. It will become a point. It will become the origin because this dimension is n. The rank is n. I am assuming the rank is n. When the rank is n, this rectangle will not be there. So the points outside they also will not be there. So the domain will collapse into a rectangle. This will be Rn. When the rank is n, the domain will collapse into a single rectangle. There won't be 3 components. Instead, there will be only one vertical rectangle. Its dimension is n. And I have already told you on this vertical rectangle, the function is 1, 1. The matrix is 1, 1. Any 2 points will go to distinct points. 2 distinct points. The domain will go to 2 distinct points in the codomain, provided the 2 points belong to the vertical rectangle. We cannot say it for other things. So it is 1, 1. The matrix becomes 1, 1. So A, when rank A is equal to n, A is 1, 1. The matrix is 1, 1. The function is 1, 1. Function is 1, 1. Therefore, if you look at this equation Ax equal to B, if you look at this equation Ax equal to B, when this B is here, because B is in the vertical rectangle in the codomain means that is the range. See, all the vectors here will be pushed into that rectangle, vertical rectangle. That is the range. That is the range. That is the image. So when B is here, the Ax B equal to B will have a solution. Ax equal to B will have a solution. When B is outside, Ax equal to B will not have a solution. Ax equal to B will not have a solution. So, when the rank is n, the domain collapses into a vertical rectangle. The horizontal rectangle collapses into a point, the origin. The third component vanishes. There is no third component. First component, second component, and the third component. So you have only one component. All the three components merged into this. And in the codomain, we do not know. We do not know anything about M. So it all depends on M. So there will be three components. But this is N, so this has to be N. This is N, this is N. So you have to remember, the whole dimension is Rm. So N is less than or equal to M. So N is less than or equal to M. Because this is also N. So N will be less than or equal to M. So when you are solving this equation Ax equal to B, when B is here, there will be a solution. And the solution will be unique. The solution will be unique because the solution will be unique. When B is here, there will be no solution. So what are the conclusions? When the rank is equal to n, when the rank of a matrix is equal to n, the equation Ax equal to B will have no solution if B is outside and a unique solution if B is inside. That is the conclusion. So look at the conclusion. And you have to go through the proof. If you don't go through the proof, you will not understand. Equal to B has a unique solution when B is in the vertical rectangle. When B is outside the vertical rectangle, the codomain, it will have no solution. So the conclusion, I am going to write it like this. When rank is equal to n, implies at most one solution. At most one solution. Why do I say at most one solution? When B is here outside, it has no solution. It has no solution. When B is inside, it will have unique solution. That is why when the rank is n, it will have at most one solution. When rank is equal to m, it will have at least one solution. Rank is equal to m. You have to argue carefully and understand that very carefully. Let me very quickly give the proof for that. Rank is equal to m, because this is very important. When the rank is equal to m, what happens? Rank of A equal to m. So this is the domain Rn. You have three components here. In the codomain, usually you have three components. Now Rm. Now the rank is equal to, I am assuming rank is equal to m. When I assume the rank is equal to m, the dimension of this vertical rectangle is m. This is also m. That whole dimension is m. That means only the vertical rectangle exists. All the other, this will collapse. The third component also will vanish. So the codomain will become just a vertical rectangle, Rm. That will be the whole dimension, whole vector space, the range. That means the function A becomes onto. In the domain, there will be no change. It depends on the value of n. Depends on n. So the codomain collapses into just one piece of rectangle, vertical rectangle. The other two vanish. So we know m is less than or equal to n. This m has to be less than or equal to n. When m is equal to n, this will also collapse into one vertical rectangle. So when the rank is m, the function becomes onto, because any b that you take, it is going to be in the vertical rectangle in the codomain. Because in the codomain, only the vertical rectangle exists. So it is going to be onto. So when rank is of m, if the function is onto, there will be at least one solution. Why do I say at least one solution? Because when it is here, when the b is here, it is onto. So at least one pre-image is guaranteed. When the kernel exists, there will be infinite number of solutions. So when the kernel is existing, there will be infinite number of solutions. So you have to remember, when the rank of a matrix is n, which is equal to the number of columns, the equation Ax equal to b will have at most one solution. When the rank is equal to m, number of rows, then the equation Ax equal to b will have at least one solution. These two results play a very important role in the problems that we are going to do. So now take problem number 1. Problem number 1. Problem number 1. Consider a homogeneous system. All of you have been given this problems. Yesterday itself, the problems were posted. Consider a homogeneous system of linear equations Ax equal to 0. Where A is an m by n matrix. A is an m by n matrix. Then which of the following statements are always true? Which of the statements are always true? Ax equal to 0 has a solution. Ax equal to 0 has a solution. So you must remember, Ax equal to 0, this is called a homogeneous system. Ax equal to 0 is called a homogeneous system. It will always have a solution. Ax equal to 0 will always have a solution. The 0 solution will always exist. So I can take x is equal to the 0 vector. So A into 0 will be 0. So the 0 solution will always exist for the homogeneous system. So Ax equal to 0 always has a solution. So read the question carefully. Which of the following statements are always true? Which of the following statements are always true? Ax equal to 0 has a solution. That is true. Ax equal to 0 has a solution. The homogeneous system always has a solution. The 0 solution is there. Next one is Ax equal to 0 has no non-zero solution. Ax equal to 0 has no non-zero solution. Ax equal to 0, third option has a non-zero solution. Ax equal to, so it all depends. See, you have to choose different matrices and argue those two cases. Ax equal to 0 has no non-zero solution. For example, supposing I take this equation. Just one equation. One equation in two unknowns. One equation in two unknowns. Now this equation has a non-zero solution. For example, I can put x1 equal to 1 and x2 equal to 2. So 1, 2 is a non-zero solution. For this system, Ax equals 0. So if he says Ax equals 0 has no non-zero solution, that is false. That is false. See, Ax equals 0 has a non-zero solution. Ax equals 0 has a non-zero solution. That is also, you cannot say always true. It's not always true. It's not always true. And the fourth one, dimension of the space of all solutions is at least n minus m. Dimension of the space of all solutions is at least n minus m. That is, you are asked to find the kernel, the dimension of the kernel space. So that has to be worked out. So let me go to the second problem. A is an m by n matrix. X and B are column vectors such that Ax equal to B. Ax equal to B has infinitely many solutions. So Ax equal to B has infinitely many solutions. So it is given that Ax equal to B has infinitely many solutions. What is the meaning of that? Ax equal to B has infinitely many solutions means you have to draw the diagram, the domain or n, the codomain or m. Here you have to draw two rectangles which are orthogonal, two rectangles here which are orthogonal. Two rectangles which are orthogonal. Infinitely many solution means this kernel of A has a non-zero vector. That is the very important point to be noted. Infinitely many solutions. Kernel is having only the zero vector. We discussed the function becomes 1, 1. At most, the kernel has a non-zero solution, non-zero vector here. That is very important. So, Ax equal to B has infinitely many solutions. Now, we have to discuss Ax equal to B dash. Ax equal to B dash. Consider Ax equal to B dash. B dash is not equal to B. So the matrix A is the same for both. The matrix A is the same for both. So the kernel of A is having a non-zero vector, whether you are solving this equation or this equation. The kernel of A is having a non-zero vector. So look at the answers, look at the different options given. First option is no solution. Ax equal to B dash has no solution. See, when B dash is here, when B dash, only then solutions will arise. When B is outside, there will be no solution. So, Ax equal to B has infinitely many solutions means B is there in the vertical rectangle. B dash, it is given B dash is not equal to B. So B dash may be here. When B dash is here, B and B dash are not equal. They are not equal. So when B dash is here, the system, so that means A, option A is false. It is given no solution. That will occur only when B dash is here. When B dash is here, there will be no solution. But when B dash is inside, it will have a solution. So option A is false. Remember, option will be true only if it is true always. In all cases, it must be true false. So option A is false. Unique solution. So question of unique solution does not arise. No possibility of unique solution because the kernel of A is not equal to 0. So option B is also false. C, infinitely many solutions. That is also false because when B dash is outside, there will be no solution. When there is no solution, no question of infinitely many solutions. So that is also false. Look at the fourth option. Infinitely many solutions if it has a solution. If it has a solution, that means Ax equal to B dash has a solution that is given. That means B dash is inside. B dash is inside. And when B dash is inside, it will have infinitely many solutions because the kernel is having a non-zero vector. So option 4 is the correct option. So you have to argue problem number 2 very carefully and understand the implications. It looks simple, but you have to argue very carefully. See, let me go to problem number 5. Problem number 5. I don't know whether I'll have time to finish all the problems. Problem number 5, let me do. So, A is an m by n matrix for which Ax equal to 1, 1, 1 transpose has no solution. Immediately you have to draw the two diagrams, the domain and the codomain. The domain with the 3 components, 2 rectangles which are perpendicular, and the codomain once again with 2 rectangles which are orthogonal, which are perpendicular. The domain and the codomain. This is the general case. Sometimes collapse will take place. For example, when the rank is equal to n, in the domain, there will be only one component. This rectangle will collapse into a point. So, the third component also will vanish. So, there are 3 components, 1, 2, and 3. For the sake of convenience, I am calling them as components. Because component in mathematics has got a definite meaning. In topology, it has got a meaning. And it has got a meaning in so many other branches of mathematics. Here I mean 3 different sets. These 2 are vector spaces. 3 is not a vector space. 3 is not a vector space. So, the domain or codomain will have 3 components, or when collapse takes place, it will have only one component. Remember, it cannot have 2 components. It cannot have 2 components. It will have one component or all the 3. So, now look at the problem number 5. Problem number 5. Ax equal to 1, 1, 1 transpose. Vertical rectangle, it may be here also. This 1, 1, 1 may be here or here. Third component or in the second. It is not in the first component. It is not in the first component. That's what you have to remember. So, Ax equal to 1, 1, 1 has no solution. That means this 1, 1, 1 is outside the first component. Ax equal to 0, 1, 0 transpose has exactly one solution. That means 0, 1, 0 is here. Inside. Only when it's inside it will have a solution. When it's outside, it has no solution. So it has to be inside. Has exactly one solution. Exactly one solution means the kernel will not exist here. The kernel has to be 0. That means the three components in the domain will collapse into one component, namely this. Only Rn will be there. Rn will be there. The three. So, exactly one solution. When the kernel exists, it will have infinitely, it will produce infinitely many solutions. So this cannot exist. So the domain will collapse into one component. And the codomain has three components. Definitely it has three components. So this is n. This is also n. Remember, the vertical rectangles are always equal in dimension. So this is n, this is also n. This is R3. Because we are dealing with three-dimensional vectors. Ax equal to 1, 1, 1 transpose, three-dimensional vector. So 1, 1, 1, 1, 0, 1, 0, they are all in R3. So this is three-dimensional. So remember, there are three components definitely. Therefore, n will be strictly less than 3. Very important conclusion. Very important. All the three components exist. So this n will be strictly less than 3. It will be strictly less than 3. Now you have to argue the various cases. Ax equal to 0, 1, 0 transpose has exactly one solution. Then m is equal to 3. That is the first option. M equal to 3. That is true because m is equal to 3. All the vectors are three-dimensional vectors in the codomain. M is equal to 3. N is greater than m. N is greater than m. See, n is less than 3. This is m. So n is strictly less than m. So option B is false. N greater than m is false. Then the third one, eta of A is 1. Eta of A. Eta of A means the nullity of A. Nullity of A is 1. Nullity of A is denoted by this rectangle, but now remember this rectangle is collapsed. This nullity does not exist. Nullity is 0. Nullity is 0. So nullity of A is 0. So that is also false. Eta of A equal to 1 is false. And the fourth option, R equal to N equal to 3. R equal to N equal to 3. N equal to 3 is not possible. Remember, N is less than 3. Already I have concluded N is less than 3. So this is also false. So out of the four options, the only correct option is A, M equal to 3. A, M equal to 3. All the other three options are false. So now let me take the last problem. So only the last two problems are slightly difficult. That's why I rushed through to complete the last two problems. Problem number 6. Problem number 6. Let T1 and T2 be two linear transformations from Rn to Rn. Both are, see, T1 is from Rn to Rn. Remember, M equal to N here. T2 also same. X1, X2, Xn is a basis of Rn. It's a basis for Rn. Suppose that T1 of Xi is not equal to 0. T1 of Xi is not equal to 0. So draw the two diagrams. All these problems, 6 problems, have to be done only using the diagrams, the fundamental spaces along with the diagrams. So, normally we'll have 3. So, you have to draw the general case. When a particular case happens, you have to change the diagram. So, T1 of xi is not, for example, take T1 of x1, it is non-zero. T1 is from here to here, Rn to Rn. T1 of x1 is not equal to 0. That means, see, if T1 of x1 is equal to 0, x1 will be in the kernel, it will be here. So, now T1 of x1 is not equal to 0 means x1 is outside, it is not in this rectangle, it is outside. When it is outside, the natural tendency will be to mark it here. That is wrong. If you mark it there, you are totally mistaken. x1 can be here or here. Remember, there are 3 components. That is why some authors use only 2 components. They don't talk about the third component because the third component is not a vector space. But I make it a point to mention the third component also. It is only a collection. Third component contains linear combinations of vectors in the first 2 components. So, when it is not here, it has to be here or here. Similarly, you take x2. T1 of x2 is not equal to 0. That means x2 may be here or here. We do not know where it is. So, it is not there. So, now look at for the other T2, you have to draw a different figure. Not the same figure. Don't mark it in the same figure. You have to draw a different one. Right? For the second one, T2, once again I have to draw 2 diagrams. 2 circles with the 2 perpendicular rectangles inside the domain and codomain. So you look at it, xi is perpendicular to kernel of T2. Xi is x1, for example. You take x1 is perpendicular to kernel of T2. X1 is perpendicular to kernel of T2 is this. This is T2. Kernel of T2. So x1 is perpendicular to kernel of T2 means any vector perpendicular to this kernel will be here. It will be there. If you take x2, that is also perpendicular to kernel of T2. So x2 will be here. So all the x1, x2, xn, they are all in the vertical rectangle for the second operator T2. For the second operator T2, all the x1, x2, xn, they are in the second, they are in the vertical rectangle for the second operator. And you know, this is a basis you are given. x1, x2, xn is a basis of Rn. So you have got n linearly independent vectors here. That means the dimension of this vertical rectangle is n. The dimension, because n are linearly independent, so dimension is n. That means for the operator T2, collapse takes place. The 3 components will collapse into only the vertical component. Only the vertical component, because in the vertical component x1, x2, all these vectors, they are n linearly independent vectors, they belong to that. So there is no second component, there is no third component. Simply it means they are 0. Second component is 0. So when it is like this, the rank of that T2 is n. The rank, because this is the dimension of this vertical rectangle is the rank. The rank is n. When the rank is n, the matrix is invertible. It is full rank. So the matrix is invertible. So T2 is invertible, but about T1 we cannot say. Sometimes it will be invertible, sometimes it is not invertible. Because when it will be invertible, when all the x1, x2, etc., when they lie in that vertical rectangle, it will be invertible. But it is not needed. x1 is not here, that means x1 may be outside. When it's outside, the dimension will not be the full one. It need not be the full one. Therefore, T1 invertible is not true because sometimes it is invertible, sometimes it is not invertible. But T2 is definitely invertible. So look at the four options. The correct option is T2 is invertible. Option B is correct. Option B is correct. T2 is invertible. T1 is invertible is wrong. Option A is wrong. Both invertible wrong. Neither T1 nor T2 invertible is also wrong. So the correct option is B. So T2 is invertible is the correct option. So I need to give you some time for asking questions. So in case you have any doubts, you can ask me. After the webinar is over, my telephone number is there in the webinar, in the Telegram group formed by the organizers. So you can go and get my telephone number. You can contact me on WhatsApp, or you can call me on the phone and discuss with me. Because in this kind of webinar, there are some doubts, clarification of the doubts is very important. So now over to the organizers for organizing the question and answer session. Thank you, one and
The
all.
participants sent some questions related to the topic, sir. Shall I ask? First
Yes,
question.
yes.
What is the difference between dimension of column the matrix?
Dimension of?
Difference between dimension of column space of the matrix and the nullity of the matrix.
Dimension of the column space of the matrix. Column space of the matrix is, remember, it is in the codomain. It is the vertical rectangle in the codomain. So, when you talk about the dimension of the column space, it is the dimension of the vertical rectangle in the codomain. But nullity means it is the dimension of the horizontal rectangle in the domain. They need not be equal. They are two different entities. They are defined in a very particular way. So the dimension need not be equal. Column space of A is in the codomain. Null space of A is in the domain. Julia.
Next question. Any shortcut
Yes.
method to find the rank of a matrix?
There is no
any
shortcut
method to find the rank of the matrix?
There is no shortcut method. There is no algorithm.
How to find the dimension of
the rank of a matrix can be defined in many ways. It can be defined as the column rank or the row rank. The best method is only by the method which I did on the board in this beginning of the webinar. Row reduce the matrix and find the rank. That is the best way. All other definitions, there are many equivalent definitions of column, the rank of a matrix, but the easiest is row reduce. Julia.
How to find the dimension of solution space AX is equal to 0?
Yeah, that is precisely what I did in the beginning. I did a problem. I took a 3x4 matrix and found the solution space of the null space. So solution space, the questionnaire means only the null space. AX equal to 0. Exactly that is what I did. You have to row reduce and give values for the free variables and solve for the basic variables, pivot variables. That is how you find the solution space. That is the problem I did at the beginning of the webinar. That is very important. Julia.
Kindly suggest some books for linear algebra related with the CSIR.
See, if you want to learn the subject very well, the fundamentals, go to Strand. Strand. STRANG. If you want to learn the subject, Strand. It's a very good book on linear algebra. There are 2 volumes. One is applications, another one is on theory. Both the books are very worth buying, but if you buy one of the 2, it's enough. You can verify. You can learn the subject very well. Very lucid examples are given, very correct examples, in a very understandable way, examples are given. But if you want to do problems in net, Strang is not enough. Strang is only for understanding the subject. If you want to do problems, then you have to go to some standard books like Hoffman and Kunz, Kenneth Hoffman and Ray Kunz, Linear Algebra. That is the standard textbook for MSc Linear Algebra. Or there is a book by Halmos, P.R. Halmos, Finite Dimensional Vector Spaces, written by Halmos. That book is also very good. But Kunz, I would say, is for solving problems in net CSIR. And there is a book by a Chinese author, Fusen Zhang. Soft copy is available with me. In case you contact me on the phone, I can send you the soft copy for Fusen Zhang. It is giving lot of worked examples, and they are very important problems for CSIR net examinations. Julia.
Give some tips to crack CSIR net exams.
See, it is applicable for all the subjects, not only for linear algebra. In Tamil, there is a proverb, Agala uluvadai vida aala ulu. When a farmer wants more harvest, he must plow deep. Like that, when you want to pass CSIR net examination, don't go wide. Don't go for too many subjects. Concentrate on a few selected subjects. Study them deeply without omitting any single problem or single theory. That is the best way to crack CSIR. Because for CSIR, there are 10 subjects. Linear algebra, complex analysis, real analysis, calculus of variations, differential equations, partial differential equations, like that. No mathematician can study all the 10 subjects. I can tell you very boldly. It is not possible for humanly possible for a mathematician to study all the 10 subjects in depth. And it is also not necessary. Because if you study 4 subjects in depth, definitely you can pass the examination. You will get marks for 200 marks. Including the choice, the question paper gives you 400 marks. Net examination question paper works out to 400 marks, including the choice. So, if you ignore the choice, if you study only 4 subjects, you will be able to answer questions for 190, 180 marks. And remember, for a OC, 100 will qualify for an open category. 100 will qualify. 100, 102, 105, that will qualify. And remember, the first All India rank in a net examination, the first student gets only 120 or 125, 130 marks. It varies from year to year. So if you get 110 or 105, that means you are a top student at the national level. For that, you have to concentrate on 10 questions in part A, 10 questions in part B, and 10 questions in part C. Because when you concentrate on 10, 10, 10,
Over to Joel.
Julia can propose the vote of thanks.
Yes, sir.
Yes.
Shall I propose a vote of thanks, sir?
Yes. Please go ahead.
Thank you, sir. After a very long time, we are hearing your lecture, sir. Really, it is very interesting, and thank you for accepting our simple invitation. Tomorrow, the session will start by 9 o'clock. Thanks to the participant.
Thank you, Ananda.
Dominus tecum, benedictus
benedictus fructus ventris tui, Iesus.